Okay, so now this is the idea behind hydrodynamics. Alright, hydrodynamics. So hydrodynamics is fluid in motion, okay, and there are two types of, alright, so that is fluid flow. So there are two types of flow. We have laminar flow, alright. The other name for laminar flow is what we call streamline flow, and we have what? Now the other name also, now when you talk about laminar flow or streamline flow, alright, it's a kind of flow that moves in a regular or irregular kind of flow, and the example, alright, is tap water. Tap water is a laminar flow, right? It follows what irregular. Then blood flow also in the vein. Blood flow in the vein, alright, is an example of what laminar flow. While turbulent flow is an irregular flow, alright, is also chaotic in what in form. So is streamline or laminar flow is regular, while turbulent is chaotic and what an irregular. Example of that is smoke. Alright, smoke undergoes a linear motion because it moves in a zigzag form. Alright, and another example is blood flow in the artery. Blood flow in the artery is also an example of what of turbulent flow. Blood flow in the vein and tap water is an example of laminar. Then turbulent is chaotic, irregular. Streamline or laminar flow is what we call irregular flow. While this one is what is irregular. And the velocity they move, which is what we call flow velocity v. Alright, every flow of a liquid moves with what we call flow velocity. Flow velocity is what is v, and that is what we use in continuity of equation. So now this is the example or the diagram of a laminar flow. So it follows a regular pattern, alright. So to the tangent, so you have a straight flow, so that is laminar, but the turbulent is chaotic, is irregular. So the flow moves in what in any manner, a zigzag or haphazard manner. So now a laminar flow, alright, has a low Reynolds number compared to a turbulent flow. A turbulent flow has always flow with a very high Reynolds number. Alright, and what is Reynolds number? Reynolds number is rho v over the coefficient of viscosity. Okay, this is the formula for Reynolds number. So you can also calculate for a Reynolds number. So Reynolds number is equal to rho is the density, v is the flow velocity. Alright, then d is the diameter of the pipe. Right, if your liquid is flowing in the pipe, then eta is the coefficient of viscosity. So what is coefficient of viscosity? Now viscosity is like the thickness of a liquid, alright, how thick a liquid is. So if I talk about palm oil and water, palm oil is more viscous than water because palm oil is thicker than water. In a simple or fundamental sense, we can explain it like that. So the formula of coefficient of viscosity, eta, this is symbol is eta, is force over area multiplied by velocity gradient, and velocity gradient is velocity over length. All right, the length, the temperature, or the quantity divided by length is what we call what gradient. So force over area multiplied by the velocity gradient is what is the formula for coefficient of viscosity, or eta is equal to F over A multiplied by velocity gradient is what is V over what over M. Alright, so that's how to calculate for that. So multiply density times flow velocity times the diameter over coefficient of viscosity will give you the Reynolds number. And I said turbulent flow, alright, flows with what? The examples are smoke and what? And blood flow in artery. But for laminar or streamline flow, regular, this one is irregular. We have blood flow in the what in the vein, then for turbulent is in the artery. In laminar, regular or streamline flow, examples are blood flow in the vein. While in turbulent, irregular or chaotic flow, we have what? Blood flow in the what in the artery. Example here is also tap water. Here is what is smoke, right? So now I said that turbulent flow always flow with what high Reynolds number, and this formula of a Reynolds number rho v d over eta, and I said eta is the coefficient of viscosity, which has a formula of eta is equal to coefficient of viscosity is equal to force over area multiplied by velocity gradient, and I said velocity gradient is what velocity over what over length, temperature gradient is temperature over length, pressure gradient is pressure over length. That is in case of Poiseuille's equation. So this is what we have, all right, for that. Now aside from this, there are two basic equations, all right. So this is how to calculate for Reynolds number. There are two basic equations we use for what's it called, for hydrodynamics or fluid mechanics. Okay, I want to write the two equations. The first equation is what we call the continuity of equation, and the second equation is what we call the Bernoulli's equation. All right, so now for continuity of equation, you must understand first of all how to calculate for the volume flow rate and the mass flow rate. So what is mass flow rate and volume flow rate? So volume flow rate, okay, of a liquid, I've analyzed the type of flow we have and how to find the Reynolds number and the coefficient of viscosity of a liquid. Don't forget I said viscosity is thickness, okay, or the resistance that that a layer of liquid experiences when it wants to move from one medium to another. Okay, you can call resistance, you can also define it as a thickness. So the first thing we need to take note of is what we call volume flow rate. So I'll prove all the equations we need. So volume flow rate of a liquid, all right, and mass flow rate of a liquid. When you say volume flow rate of a liquid, what does it mean? Volume flow rate of a liquid is change in volume per change in time. All right, while mass flow rate is change in mass per change in time, and this one is given, the symbol is Q, and it's what? Area multiplied by flow velocity. Okay, this volume flow rate. Don't forget, volume flow rate of any liquid is what? Is the change in volume per time taken. The symbol is Q is equal to area multiplied by what? The flow velocity. So if that is the case now, okay, so we can have our continuity of equation from that place, which is what? Q, all right, because we are using a pipe. All right, we are using a pipe and the flow of liquid in and out of the pipe. Now for the first pipe, we can have area 1 and flow velocity 1. All right, we can have area 2 of the pipe and we can have flow velocity 2. So at the end, if you combine them together, you have water flow in the pipe is equal to volume flow rate out of the pipe. This in and out. All right, so what's going to happen? Q is what? AV, right? That is what? AV in the pipe is equal to what? AV, what? AV out. So at the end you have what? A1 V1 is equal to what? A2 what? A2 V2. So this equation is what we call volume flow rate. All right, volume flow rate dV over dt. Why A1 V1 is equal to A2 V2 is what we call the continuity of equation. Continuity of equation. So that's what happens. All right, so A1 V1 is equal to A2 V2 is continuity of equation. All right, so then what is mass flow rate? So don't forget, volume flow rate is dV over dt is equal to Q is equal to area multiplied by flow velocity. Flow velocity is in meter per second. Why continuity of equation is area 1 flow velocity 1 is equal to area 2 flow velocity 2, and these are the formulas for constant of viscosity and Reynolds numbers. So now when you talk about mass flow rate, which is the second before I analyze the Bernoulli's equation, what do we mean by the mass flow rate? Now, once volume flow rate is changing volume per time taken, mass flow rate will be what? Changing mass per time taken. Volume flow rate and mass flow rate. So mass flow rate is changing M divided by what? Changing T. All right. And when we're doing hydrostatics, if you watch hydrostatics video, you'll find out that we said that density is equal to mass over what? Volume, and what? Rho v is equal to the what? The mass of the object. So that means mass is what? Is rho v. Now, if mass is equal to rho v, density multiplied by velocity. If we are talking about mass per time now, so you now have what? Change in m per change in time is equal to rho, all right, multiplied by change in v over change in time taken. That's what we're going to have. Change in m, your mass is density multiplied by volume. Change in mass per change in t will now be equal to density multiplied by change in volume times change in t. So you have dm over dt. You can prove your equation from that. So you have equal to dm over dt is now what? Rho multiplied by what? Change in v over what? Over change in t. Okay, so what is dm over dt? The mass flow rate dm over dt is equal to rho multiplied by, what is dv over dt? Your dv over dt is equivalent to what? Q is equal to AV. So you have change in v over change in t is equal to Q is equal to AV. So anywhere you see it, you can write it as what? As Q. So you have mass flow rate dm over dt is equal to rho multiplied by your Q is now what? Q is equal to AV. So you have what? AV. So your change in mass per change in time taken is equal to rho what? Rho AV. So if you have to find the mass flow rate, multiply your density times the area, then times the flow velocity. Okay, then don't forget that I said we are having in and out of the pipe, so you can also determine the value of what? Of the mass flow rate. All right, in and what? And out. So we have dm over dt, this what? This in, and this what? This out. So if this is the case now, what is dm over dt of in? So you have what? Rho AV, because dm over dt is equivalent to what? AV. Dm over dt is equal to rho AV. So you have rho AV in is equal to rho AV what? AV out of the pipe. So at the end you have what? In terms of initial and final, A1 V1 is equal to what? Rho what? Rho 2 A2 what? A2 V2. Density 1 flow area 1 flow velocity 1 is equal to density 2. All right, then area 2, then flow velocity what? 2. This is like the third equation, this second, this is the third what? Third equation. All right, that's what we call the final equation of mass flow rate. So don't forget all of this. We have volume flow rate and we have the mass flow rate. Okay, volume flow rate is dV over dt is equal to Q is equal to AV, area times flow velocity, and from that place we have the continuity equation, which is A1V1 is equal to A2V2. This when you're using a two-boy pipe, then we also analyze the equation of the mass flow rate, which is given finally to be rho AV, alright, but if it's in two different forms, you have rho A1, rho 1 A1, alright, V1 is equal to rho 2 A2 V2. Okay, so that is how to basically analyze that. So alright, so that's the first thing we need to, the first equation we need to understand about fluid mechanics. Then the second equation is what we call the Bernoulli's equation. Okay, the Bernoulli's equation. Now, Bernoulli's equation, or the idea of Bernoulli's equation, actually talks about the fact that in an incompressible non-viscous fluid, alright, in an incompressible non-viscous fluid, the pressure, alright, plus kinetic energy per volume, alright, plus potential energy per volume is constant. That is Bernoulli's equation. Pressure plus kinetic energy per volume in an incompressible non-viscous fluid. Pressure plus kinetic energy per volume plus potential energy per volume is what? Is constant. So what we're going to have at that particular point, so we are going to be having pressure plus we have kinetic energy per volume mathematically from Bernoulli's equation plus what? Potential energy per what? Per volume is equal to what? Constant. So that is that. But your K is a form of mechanical energy, is 1 over 2 mv squared, while your potential energy is equal to what? Mgh. So if this is the case, then from Bernoulli's equation we state that in an incompressible non-viscous fluid, kinetic pressure plus kinetic energy per volume plus potential energy per volume is equal to constant. You now have pressure plus your kinetic energy is now 1 over 2 mv squared over volume, alright, plus potential energy per volume, that is what? Mgh per what? Per volume is equal to what? Constant. So, but mass over volume, density is equal to mass over volume. Okay, if density is mass over volume, it suggests that anywhere you see density, impute to what? Mass over volume. So you have pressure plus, this is 1 over 2, mass over volume is now what? Density, V squared, alright, plus this M over V, mass over volume again will give you what? Density, because density is what? M over V is equal to rho, alright, or rho is equal to what? M over V. So this M, so what I'm going to have is what? Plus another mass of volume will give you what? Rho GH. Everything is equal to what? Is equal to constant. So that is the expression of what? Bernoulli's equation. So you have altogether pressure plus 1 over 2 rho V squared plus what? Plus rho GH is equal to what? Is equal to constant. So if it's in terms of two different alright form, like we did for both continuity of equation, volume flow rate and mass flow rate, what's going to happen? You have what? P1 plus 1 over 2 rho V1 squared, alright, plus what? Rho GH1 is equal to, so you do constant P2 plus 1 over 2 rho what? Rho V2 squared, okay, then plus what? Rho GH what? Rho GH2. That is the final